estimate it by y sub j superstar, and this is the moment for this. So this is the moment for this entire thing. You pretend that everybody isn't variable, that they all have this value. And that's the density times the area. Delta A, dA, whatever you want to call it. So, blah, 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 send n to infinity, the whole deal again, and you get, so we got this total mass, which ended up being that. This is equal to the double integral over d of y rho of x comma y dA. And in a similar argument, and that's the moment about the x-axis, or the moment to the x-axis. And again, it's almost like torque. It's the tendency of, I always think of it again as a DAC, of that to collapse. How much total weight it's handling. And like, the distance here is y sub j. So now when we talk about the moment to the y-axis, it's this distance, which is x sub I superstar, times the density times the area. Density times the area gives you the mass in that little area. Okay? So, not to bore you, but just say similarly, the moment to the y-axis is denoted by m sub y, where m sub y is equal to the double integral over d of x rho of x comma y dA. I'm trying to keep that analogy, but I'm out of space, so. So the mean, or the average, or the center, is the sum of these guys divided by the total mass, which I cleverly just erased. So x bar is y m sub y over little m, and y bar is m sub x over little m, or double integral x rho of x comma y over d dA over double integral of rho of x comma y dA. Y bar equals m sub x over little m, double integral over d, y rho of x comma y dA. And this is just like the moment I'm so stupid that I erased that. I had it right in front of us. It's the distance times the density at the point times the area. X bar comma y bar is the center mass of this lamina. So do I want to go back to that one, or do I want to do a different one? Now I have a different one. Let's, in the interest of not boring you too much, let's do this. Let's find the center of mass of this thing. With that, where's my variable density function? What was x squared?
Yeah.
Because we already got the total mass, and I could tell it's nothing earth shattering here.
And that's the total mass.
Okay, so total mass was 3.15. Okay, so we want, e.g., find the center mass for the above example. Little m was double integral of x squared over d of dA, which is 3.15. So it's the sum of the y, each x point. Can you envision what's going on here? How you're going around each x point and measuring the distance from the x-axis? That the distance, I'm sorry, from the x-axis, right, is a y quantity. So that's a mistake, isn't it? Oh no, that's x bar is the distance from the y-axis. That's right. That's right. That's the distance from. That's right. No, I got it right. From the y-axis. Okay. So I got the integral from -2 to 1 of x cubed. Let's go dy dx, and this way I have to set up. And so that's x cubed y from x to 2 minus x squared dx, which I have calculated out to be. I calculated out to be negative 18 fifths. Negative 18 fifths. This one, which I have calculated out, how did that become a y? Oh, because it's dy. So I did the one iteration, then decided to stop. This is x. Not that you don't care. I know you know the answer. X squared over. So that's x squared, y squared over 2, yeah? From x to 2 minus x squared dx. So that's the anti-respect to y. And so I did one iteration, and I calculated that out to be negative 9/7. Therefore, x bar equals negative 18 fifths over 3.15, which gave me negative 1.14. Y bar is negative 9/7 over 3.15, which gave me negative 0.41. is it, like about here? So that's where if you put a point, that oddly shaped lamina would balance. Thin plate with that variable density. It's a variable density that, you know, like if it was uniform density, it would probably be about, where would you put it if it was uniform? About there?
It's almost close to there, but
Right.
consider the
It's uniform, you see it like, you know, like when you, we've all done it, you know, tried to balance a plate on our finger or whatever, and it goes in the middle, but you put a cupcake on the side of it, and you gotta move your finger around, right? So, that's the center of mass. Which means that the sum of all the moments can be thought of as being concentrated right there and would have the same effect on the stress. That's the way I always thought of center of mass. Put everything right there in the center. Okay, so this is going to push into 3 dimensions next. So I wanted to get the theory done, and then go into triple integrals. And again, we could redo this whole discussion, and if you guys are interested in electricity, we could think of it as total charge, and have that discussion. Then the next one is moments of inertia, which is just distance squared. Okay? The only change in the whole discussion is that this guy gets squared. You know, the applications to moments of inertia is up to your physics, you know, classes at that point. But the moments of inertia is the same discussion, only you redefine it as distance squared times the mass. Okay? So that leads into that, but I'm not going to bore you with that. That's the thing that keeps. And these guys always screwed me up. I always have to draw the picture because the moments around y are the sum of your x's, and the moments around x are the sum of your y's. This is what measures distance, x values. This is what measures y values. So when you talk about this guy and this guy, the notation gets a little goofy. I'm not going to require you to memorize that stuff. If I ask that question on an in-class exam, I'd give you the formulas.
There's only 60 minutes of memory on that.
Oops.